Hello, it's 5 o'clock sharp Swiss time. With great pleasure, I welcome all of you on behalf of ISI, the International Space Science Institute in Bern, Switzerland, to today's talk in ISI's Game Changer series. I'm Joachim Wamskans, Director for Astrophysics and Cosmology at ISI, and your host today. ISI has been serving the space science community for a quarter of a century by offering various tools for scientists to meet in Bern and jointly do science related to space missions. In July last year, we introduced the ISI Online Game Changer seminar series as one of a few new tools because physical meetings in Bern were not possible. After a short break in spring, we restarted in May. We have had a talk every Thursday with 2 more to come. In case you missed any of our previous 37 talks, they were recorded and can be viewed on the ISI website. Before we start with today's talk, let me announce next week's seminar. Corinne Le Carré from the University of East Anglia, UK, will talk about the contemporary global carbon cycle and the impact of the COVID-19 pandemic on CO2 emissions. We are very happy to have Reinhard Genzel as today's speaker. Reinhard is an infrared and submillimetre astronomer. He and his group are also engaged in developing ground and space-based instruments for astronomical observations. Reinhard had studied at Freiburg and Bonn University, the German Freiburg that is, and as a side note, Reinhard was then a very promising track and field athlete. His specialty was javelin throw, Speerwurf. He was even handled as a candidate for the Munich Olympics in 1972, but then he decided to concentrate on astronomy. He finished his PhD in 1978 at the Max Planck Institute for Radio Astronomy in Bonn. As a postdoc, he worked at the Harvard-Smithsonian CFA in Cambridge, Massachusetts. He moved to the UC Berkeley as a Miller Fellow, was promoted to associate, and in 1985 to full professor there. In 1986, Genzel became director at the Max Planck Institute for Extraterrestrial Physics in Garching near Munich, and in 1988 also honorary professor at Ludwig-Maximilians-Universität. He always kept his joint appointment at UC Berkeley. Reinhard has won numerous prizes. For example, in 2011, he received the Karl Schwarzschild Medal of Astronomische Gesellschaft. In 2012, the Tycho-Brahe Prize of the European Astronomical Society. In 2016, the Herschel Medal of the Royal Astronomical Society. And as you all know, last year, Reinhard Genzel was awarded the 2020 Nobel Prize in Physics, jointly with Andrea Ghez and Roger Penrose, for the discovery of a supermassive compact object at the center of our galaxy. Without further ado, I'll hand over. Reinhard, the screen is yours. We're all very excited to listen to your talk on testing the massive black hole paradigm with high resolution astronomy.
Well, thank you. Let me then go to my talk. So what I will do today, colleagues, is to tell you about a road trip. A road trip which is ongoing, I should say. And it has been going on for me for 40 years. And the purpose of the road trip is to do something which we are supposed to be doing as experimentalists for a long time, actually, namely to test general relativity in a regime where the theory predicts objects called black holes nowadays, objects where no communication is possible from within the so-called event horizon, and where presumably the mass and energies are confined to a very small, the theory says even an infinitely small region in the very center in a singularity. So these almost absurd type objects were predicted in the theory, of course, 100 years ago. And within a few years after the initial work, the first solutions appeared. And as you know, Schwarzschild in 1916 was the first one to solve the problem of a spherically symmetric, non-rotating mass distribution, and found that if such a mass distribution was sufficiently compact, then there's a characteristic radius which is proportional to the mass of the object, within which not even light can escape. So that's the black hole. It then took another 50 years to find out more theoretically about these objects. Roy Kerr in '63, for instance, found a solution where in addition to the mass, there's also rotation. But no more is needed to describe these objects. And in fact, Roger Penrose, with whom I shared the Nobel Prize last year, was the one to generalize the concept of such possible objects to a very general set of topological problems, such that symmetry really doesn't play any substantial role. And then, of course, since that time, the theory has been expanded, and people are now, of course, wanting to include quantum theory in it. That has not yet worked, but it's clear that there are properties of the black hole which still need to be combined with quantum theory. I mean, I mentioned already the central singularity as a conundrum, which may have to be changed if the proper quantum theory is found. And the other one is the issue of information. According to the general theory of relativity, it doesn't matter whether you throw refrigerators or rocks or planets into the central part of a black hole. It's all the same after they have arrived at the mass center. That is not so in quantum theory, we are sure, and those quantum numbers should still be available as an information and perhaps also accessible. So that's the theory, and the question is, might such objects exist in the universe out there? And the first piece of evidence also came in the 1960s, and that was the discovery of the quasars. Quasars are radio emitting objects, which then in optical light turned out to be very compact star-like objects, therefore the word quasar, quasi-stellar radio sources, and were emission lines in the spectrum when observed with the Palomar telescope by Martin Schmidt, showed redshifts. The first one was a redshift of 15%, which, if interpreted as an expansion redshift of the universe, is equivalent to 2.4 billion light years, which means that if you convert the amount of light seen into a luminosity, that this faint star, which one had discovered, was about several thousand times brighter than the entire Milky Way with its hundreds of billions of stars. So how could these objects actually be so bright? It was pretty clearly unlikely that they were stellar in origin and fusion their source because of the enormous amount of energy radiated. But then the possibility of accretion of material onto massive black holes became an ever more possible hypothesis. Basically, the idea is that while, as I'd explained already, there's an event horizon from within, you cannot send even light anymore. On its way in, any particle falling in would convert or might convert gravitational energy into radiation. And since the amount of radiation could be very large just outside of the event horizon, one could then explain quasar-like luminosities if the object we are talking about has, say, 1 billion times the mass of the sun. So that was the birth of the so-called quasar paradigm. And of course, the question is, how can we prove that? Before I go on, let me say there's a second type of black hole candidate were discovered at pretty much the same time by X-ray astronomers, finding bright X-ray sources in double stellar systems where one of the stars was a normal star or even a big star, whilst the other one was obviously not shining in normal radiation and was likely a stellar mass black hole fed by material from the other star. So it's these types of black holes which were the candidates for the observational astronomers. And going back to the quasars, the question was how to prove the hypothesis which which was raised of accreting massive black holes. How can we do that? And I'll try to explain to you how that method might work. Now, it took quite a while between the 60s and the situation where we are in now, where within, I would say, about a period of 2 decades, the observational situation has dramatically changed from one where we had some hints to a situation where we have very strong evidence that indeed the quasar paradigm is correct. The one I'm involved in, and which I've been sharing on this path with Andrea Ghez from UCLA, is the story of looking at the nearest galaxy we have, namely our own, and look at stellar motions and gas motions in the Galactic Center to exclude with ever better measurements that there is to exclude any configuration other than the black hole for the object we are finding there. Another tremendous breakthrough, of course, happened when the LIGO community discovered 6 years ago radiation from an inspiraling stellar black hole system with high mass. And of course, in the meantime, many such systems have been found and validated the predictions from the 1960s. Finally, the radio astronomy community also has made terrific progress in using photons as a way to get very close to a black hole by looking at the innermost region where, again, the light should not be able to orbit around the black hole, but fall into it, and thereby creating what one would call a shadow, a central dark region within, just outside of the event horizon, which one might observe. And their observations in M87 seem to, in fact, fall quite nicely onto the prediction. We are hoping to see such observations also for the Galactic Center, and I'll come back to this issue. But now the general question, of course, is what it is about these black holes, and just for those of you who are not experts in the field, let me just make some very simple arguments about the black hole and how one would observe it. If you think of the sun as an object, then of course the gravity on the surface of the sun is determined by 2 quantities. One is the mass of the sun, and the other one is the size of the sun. So the larger the mass, the larger the gravitational pull, and the smaller the size, the larger is the gravitational pull. So that if you have our sun and you have a fiducial spacecraft, which you would launch into space, from its surface, you would need to have an escape speed, an initial motion of about 600 kilometers per second. Remember, in the case of the Earth, that same speed is 11 kilometers per second, or 39,000 kilometers per hour. So now let's, in our Gedanken experiment, make the sun smaller. Let's keep the mass constant, but let's make the mass smaller. And let's make it as small, as compact as 3 kilometers or smaller. And then you can easily calculate that the rocket then would have to move with 300,000 kilometers per second. And that's not possible because we know that the speed of the light is the largest communication speed. So we would have to conclude that an object of that size would have a characteristic radius, again, that is called the event horizon, which is proportional to the mass, from within which there is no more communication. So then the question is, how would you know that there is such a black hole? Well, you use its gravity. Think in terms of the analogy of the solar system. If you remember that Tycho Brahe was measuring the motions of the planets around the sun, then we have Kepler's laws, which say that the closer planets move faster and the more distant planets slower, and the velocity goes like 1 over the square root of the distance from the sun. So by proving Kepler's laws, or Newton's laws, if you like, you can then show that there's a central object, we can measure its mass, whether or not the object shines. So in our Gedanken experiment, we've now excluded radiation to come from the sun, and still you could measure its mass and also its approximate size from the motions of test particles around it. And that's exactly what astronomers have tried following the discovery of the quasars. Now, to do such an experiment, say with stars or gas around a quasar is very difficult. It's possible just barely now, but at the time was not possible. You have to go closer. So that's where two astronomers came in, Donald Lillenbell and Martin Rees, who said, well, maybe black holes like the one in 3C273, which was the first one discovered, are common. It's just that only a few accretes a lot so that you can see it. If that were the case, and maybe even all galaxy nuclei had such an object, then also our own galactic center might have such a black hole. And then, of course, because that's 20,000 times closer to us than any distant quasar, we might use stars or gas in the center of the Milky Way to make such measurements. So that was really the start, if you like, of using the Galactic Center as a laboratory to test the paradigm of massive black holes. Now, it's not quite as simple as we might think, because there is dust between us and the Galactic Center, so much dust that we cannot use optical light, and we have to measure at longer wavelengths, radio wavelengths, or infrared wavelengths, or shorter wavelengths, X-rays, to look at the Galactic Center. But that's a technical matter, which of course one can overcome with technology. And I'll mention the role of technology in this research in a minute. Now, the radio astronomers soon discovered that there was indeed a compact radio source called Sagittarius A star in the central region, where the stellar density is about 1 million times larger than in the solar neighborhood. So this, what you see here is a infrared image of the central few light years in different colors. And then the radio astronomers discovered that in the middle of this is a source of radio emission, millimeter emission, which is extremely compact. We now know it to be more compact than about 40 microarc seconds. So that would fit the bill of being a massive black hole or its surroundings located at the center of the central star cluster. Now, how about evidence for a mass concentration? Well, for that, we need to, to get a tracer, as I discussed. And the first tracer used was gas. There is ionized gas, which you see here in pink, and also neutral gas in green, which swirls around the radio source in the central few light years. And Charles Townes, Nobel laureate for the invention of the laser, in his later years at Berkeley, with his students John Lacey and Gene Sarabin, and then I joined as a postdoctoral fellow, began to use infrared spectroscopy to look at the motions of the gas clouds. And indeed, what we found were that whilst the mass enclosed within a given radius increases as you go from large distances to small distances, which is what you see on the left side, which is characteristic for an extended mass comprised of the stars, actually. As you go within a few light years, so in this innermost region, the motions of the gas clouds would indicate a constant mass of a few million solar masses. So more than the stellar radiation would indicate. So that was the evidence we had in the late 70s and the early 80s in the Galactic Center. And in fact, we wrote a Nature paper in '85 where we were pretty proud to say there is very likely a 2 to 4 million solar mass black hole in the Galactic Center. So were we done? We were not done, because as the scientific principle tells us you have to not only convince yourself, you have to convince everyone else. And most everyone else didn't believe it. Why not? Well, because gas clouds do not only react, of course, to gravitation. Ionized gas can be pushed around by magnetic fields, and also neutral gas and ionized gas can be pushed around by stellar winds, which in fact do occur in the central region. So people felt one had to have a better tracer of gravity. And the best tracer one might think of are the stars themselves. So the stellar motions would be a better thing to do. And the second thing is, whilst we did measure a few million solar masses within a few light years, that is on a scale of about 1 million times the event horizon size of a hypothetical few million solar mass black hole. So there's a lot of volume in there, which might contain faint stars. You could think of a cluster of neutron stars, and some people even speculated dark matter as a possible solution for this mass concentration. So it's clear that for experimentalists like ourselves, the job was to go and measure stellar motions and go to more closer to the central radio source and investigate the motions there and see whether the hypothesis would hold up. So that's what we started actually doing when I moved from California to Max Planck Institute here to start building instruments which could do that. And that required new types of imaging detectors because, of course, as I mentioned, optical measurements are not sufficient, and they were initially not available, but then became available from the American military, then to the Space Telescope, Hubble Space Telescope, and then we were able to get them in Europe. Nowadays, I should say, ESO, the European Southern Observatory, and we are developing such detectors specifically for astronomy, but back then that was not possible because the enormous cost. The next big issue is the atmosphere. If you have a distant star and the radiation from that distant star moves through the atmosphere, the wavefronts are distorted. And that means that the images from the stars are smeared, and you can take as big a telescope as you like. The images will all be an arc second or so in diameter. And the solutions to overcome this is adaptive optics. You basically measure the distortions of the wavefronts, and then you have a deformable mirror in the path, and you undo what the Earth atmosphere has done. So that technology we developed and others developed and put it into reality in the 1990s. And then, of course, you can have a situation where initially you have this very distorted image, and you switch on the adaptive optics, and you get indeed a compact diffraction limited images, which for a modern 8-meter class telescope is about 50 milliarc seconds in diameter. So about a factor of 20 or so better than the best seeing limited observations. I should add that having a star which is bright enough to do that correction is not trivial. In fact, there are very few such stars. So another technique had to be developed, which is to develop artificial stars. We do that by taking a laser tuned to the sodium D line and then focus such a laser in the upper atmosphere at about 90 kilometers, where meteorites, which enter the atmosphere all the time, get smashed and contain some amount of trace sodium, and the sodium atoms in this upper layer of the atmosphere then are used to focus the light and use resonant backscattering to then use the radiation which is coming back as an artificial star. So the message here is to make the progress, which in fact we have been able to do in the next decades over that what we had done initially, really required constant improvement in technologies, as you will see, better telescopes, larger telescopes, and even going to a new technique which we had not been able to use before, namely optical interferometry. Also in terms of the spectroscopy, which gives you the Doppler motions of gas and stars, we developed integral field spectroscopy, which allows you to, in coupling with adaptive optics, to get diffraction limited field spectroscopy to look at the stellar spectra near the central region. So armed then with these new technologies, our group started in 1992 to use the then new ESO telescope NTT, which is a 3.5 meter telescope, a technical precursor of the VLT. And in 1995, a few years later, our colleagues at UCLA, Andrea Ghez, Mark Morris, and Eric Becklin, started to use the Keck telescope, the 10-meter telescope on Mauna Kea, to look at the stars and made diffraction-limited images. So then the idea basically is you make an image in year 1, which here would be in red, in year 2, which here it would be in green, and year 3 in blue, and then you would hope to see a change in the position. And indeed, on this image here, which is about a light month, which is a green circle around Sagittarius A star, which is the green cross, you do see that stars near the green cross show substantial changes in position. If you look a little harder, you can also see that Kepler's laws are working, because the stars very close show a large amount of change in position, while as you go away from the central source, the stars become wider, meaning that the motions are smaller. Now, if you look at the magnitude of the motions, then you can see that the motions very close to Sagittarius star move with 1,000 to 2,000 kilometers per second. So now you use the same laws of gravity, which Kepler and Newton knew, and calculate the mass, v squared times r over g, and calculate the mass. And what comes out is a few million solar masses. The same mass which we had seen 10 years prior with the gas clouds, but now with the better tracer, the stars, and also a bit closer than what we had been able to do with the gas. So we were on a good track. And the next thing also happened, our colleagues from UCLA found exactly the same thing. Scientific principle says that's a good thing if you have two groups doing the same kind of experiment, but independently, and get the same result. Then much more likely, or actually then very likely, you have the right answer. So we knew by the mid-90s that indeed there is such a mass concentration on the scale of light months and a few million solar masses of that. And that was indeed likely to be a black hole. But the same question arises, must it be a black hole? And the answer is no. Again, we're still at a scale of a few 100,000 times the event horizon size. So there could be a lot of other stuff which is dark and not stellar, which is hidden here. So we need to come closer still. Also, as you see, the motions of the stars we have done here is a statistical measurement of the mass, because we measure the velocities on the sky, two motions. We measure the motion along the line of sight through Doppler velocity, and we measure two positions. But to fully determine the motion of the star in a potential, you actually need to measure 6 coordinates. The z coordinate, that is not known, of course, since you have just a projection on the sky. Or alternatively, you have to measure more than just the motions. You have to measure the accelerations in order to then extract the true mass within the radius of the orbit of that particular star. So we would like to get orbits. That was clear. But the orbital timescales can easily be estimated to be hundreds of years. So that's hard and impossible for individual scientists, obviously. But then nature helped us. Nature helped us by giving us some stars which are so close on scales of the solar system that you can measure their accelerations, and as you will see, even full orbits on a human lifetime. And in fact, in 2000, Andrea published a paper in Nature showing for 3 stars the first accelerations. and also the first orbits. And one of them, S2, or she calls it S02, the red one, clearly was moving likely around Sagittarius star in the focus of an elliptical orbit of a time scale of somewhere between 10 and 50 years. So that would be something where we likely would be able to see a partial orbit. And so both groups then were extremely lucky that already 2 years later, we saw the star S2 go through a peri motion around the radio point source Sagittarius star. On this image here, the blue points are the measurements from our group, and the red points are from the UCLA group. So again, you see we are measuring the same thing. And the star went through the peri in 2002 at a distance of a mere 17 light hours. 17 light hours is about 120 astronomical units, or about four times the orbital radius of Neptune. So that's really solar system scales. And again, v squared r over g, v squared now, or the velocity, turns out to be about 7,000 kilometers per second at this nearest point, and 17 light hours, and you calculate the mass, and you find, well, the same mass we had before, a few million solar masses, but now within only about 1,000 times the event horizon size. We really had squeezed the possibility of alternatives quite substantially. And at that point, I would say many people were quite persuaded that the Galactic Center indeed is the best case we have for the existence of the massive black holes. And that included the physics community, not just the astronomy community. So the question is, again, are we done? Should we go ahead and do something else? Look at birds. Well, you could, but we were intrigued because the star had an orbital timescale of only 16 years. So we knew it would come back in 2018. And we felt that if we could improve our equipment still further, then we could not only measure the orbit, but we could actually see deviations from the Newtonian physics and test general relativity. So about 2005 or so, when the star already was at near Apo up at the top, we proposed to ESO a new instrument called gravity, which would combine the light of all the 4-meter telescopes on the mountain and thereby create an interferometer. But let me, just before I go there, just summarize this first phase to tell you that, of course, we didn't only see one star. We then began to see quite a number of stars and measured their orbits. And it's an absolutely beautiful case of astronomy as well, because what we found was exactly what we wouldn't have not expected. Every theorist would tell us that there cannot be any young stars in this central region because any interstellar cloud could not collapse in the presence of the tidal forces of the black hole. But that's not what we observe. In fact, we see a disk-like configuration, which you see of O and B stars and Wolf-Rayet stars a little further out. And then we see B stars going very far in on these solar system scales. So you can only ask, heck, who put them there? Because normal two-body relaxation would be much too slow to put the stars there. So that has been a tremendous riddle, and at the same time has given us fantastic information on the nuclear star clusters, which also is, of course, important for other nuclei. I don't have time to go into the astrophysics here and just go on, but just tell you that this is a very important aspect of this work too. So summarizing the situation before the star came back for its next peri in 2018, we had over time done what we wanted to do. We had gone from gas dynamics to stellar dynamics, and we had gone to the 8-meter telescopes and worked with adaptive optics. And as you see, the measurements got more accurate from a factor of 2 down to about a few percent accuracy in the mass. And we had on the right side there now constrain the mass to be within about 100 Schwarzschild radii, such that other possible configurations like neutron star clusters, fermion balls, etc., could be excluded. There was one configuration, which very speculative configuration, which was still possible. That is a so-called Boson Star, an object, say, of Higgs bosons of a few million solar masses, but just bigger than a black hole, so it wouldn't collapse into a black hole. Such object we now think is unlikely to be stable, because any kind of accretion onto such an object would, after a little while, lead to a collapse to a stellar black hole, to a massive black hole. So anyhow, we were by 2017 very certain and looking forward to the next chapter, which in our case, as I said, included the building of gravity over the past decade, which was an enormous undertaking of about 100 people led by Frank Eisenhower, of several institutions in Germany, at the Max Planck Institute for Astronomy in Heidelberg, the University of Cologne, the two observatories in Paris and Grenoble, the University of Lisbon and Porto, and also, of course, the European Southern Observatory. So this collaboration then built gravity, which combines the light of the four 8-meter telescopes. So instead of a 8-meter diameter, you now have an effective telescope of 130 meters in diameter. And we hope that this would give us the corresponding jump in resolution, about a factor of 20 in resolution and another factor of 20 in astrometric precision. But that comes at a price, and I want to show you the price instrumentally, what you have to do to go that way, because it's really something which I have to say we are very proud of, that we managed to make this big step. We call this little movie the unfortunate last millisecond of the tortured photon. And you will see in a second why we say so. So here's our photon, our light comes into one of the telescopes, bounces on the primary, secondary, and tertiary. And now we have to bring it underneath the telescope to the so-called Cudeo room, where we actually do the adaptive optics, because we do have to flatten the wavefront for each of the four telescopes. And this is the adaptive optics bench, which we have in each of our four telescopes. And the four telescopes bring the light together, where in fact also the geometric path lengths has to be compensated for in these tunnels. And then the light enters the beam combiner instrument, gravity, where we have to do further manipulation in order to get the light coherent, and also to make sure that we can find the fringes. In the optical or in the infrared with a fairly substantial bandwidth to get high sensitivity, the fringes are only a few nanometers wide, if you like. And so you have to really make sure that the fringes do not get distorted by the Earth's atmosphere. The trick to do this is to phase reference to a nearby star. So you split the wavefront or the images into two and pick up an image from a nearby bright star, which you use for the tracking, and then from the science star for the measurement. To do this effectively, it's important to make the measurements at low temperature and make everything very compact. For this reason, we go into monomode fibers, which you see here. Here in these monomode fibers, we can also correct the fringes for distortions. We can also correct the polarization of the waves so that be optimum by torting and stretching the fibers for the four different telescopes. And then finally, the four beams from the four telescopes come together. And now, like in a radio telescope, you combine them in a chip initially developed for communication industry, where you make all the combinations from the four telescopes to 6 baselines, then you sample each baseline 6 times. For the phases, you separate the light into a spectrometer and finally record the fringes. So that's what you have to do. You have to also send out lasers across the entire instrument back to the telescope to measure all distances to about 10 nanometers accuracy, so that you can actually ensure that this interferometer works. But it does work, and it makes a hell of a difference. And let me show you why. So this image is an image of the central light year, again, in infrared light, which you would get on a moderately sized telescopes in seeing limited conditions. So the splotches you see are stars, or actually combinations of stars with about 1 arcsecond resolution. That's the best you can do under normal conditions. So then, of course, the adaptive optics gives you that image, which has this factor of 20 better resolution, 50 milliarcseconds, allows you to measure these motions, which I already showed you. Now, if you look at S2 in 2018 here, and more accurately, you see it's a little distorted. The image is not round. Why is that? That's because a beam of an 8-meter telescope, 50 milliarcseconds here, actually is confused. There's S2, the star, but there's also more. There's the black hole itself. Sagittarius A itself is an infrared emitter, and there may also be other objects. So that means that if you want to make very accurate measurements, you have to go to higher accuracy. So you then go now to the interferometer, and that's what you see. That's an image, in fact, of taken about last week of the Galactic Center. And you see where there was one star, you would think, in the center of 100 milliarcseconds, or about 100 astronomical units. We see 1, 2, 3, 4, 5 objects. The central one, the yellow one there, that's the black hole. Then you see 2 stars, which clearly are moving with very high speed. In fact, this object labeled K equals 17 is a 17th magnitude star, which is at about 80 astronomical units at that time, and moving at 9,000 kilometers per second. So even further in that S2, and moving very, very fast. We'll see about the star in a second. And then there are stars which we didn't know about, like this 19.7 magnitude star. I should say that the technique not only gives us higher angular resolution by a lot, a factor of 300 compared to where we started off with seeing, but in addition, the sensitivity is fantastic. In the radio astronomy, of course, has been using interferometry for many years, but the infrared optical interferometry is more difficult by about 100,000 compared to radio interferometry, just because of the wavelength differences and the fringe sizes and so forth, vibrations and all of this. But what you see here is a level of interferometry which is about 10,000 times more sensitive than anything which was done before, because of the various developments in gravity. So equipped with these kinds of superb imagery, we can now go back and look at our star cluster and look at the central part of it. And as it is, 3 years ago now, the blue star, that is S2, had its peri at 120 AU, and is now in the upper part of the orbit already again. And this year, we had peris, or we are having peris of another 3 stars, I should say. Okay, the brown objects and the green objects, and then the red objects. The red object is the one which you saw moving at 80 astronomical units with 9,000 kilometers per second. This object has a very highly elliptical orbit. Why is it interesting to have all these stars? Well, first of all, by having so many objects, we can now determine the potential more accurately and also eliminate all kinds of possibly important systematic effects having to do with the calibration of the reference frame, any kind of motions of 0, 0, etc. So we can then really look for deviations from Newton's orbits. Now let's look at the center part. So the cross is where Sagittarius A is, and then you can see the various orbits, the blue orbit of S2, the pink red of S29, and then the green brown of S55. And I leave off the green one there. And basically with these three orbits alone, we can really get high precision measurements. And we can measure the motion not anymore from year to year or month to month. We can measure it from night to night. Here you see what happened during the S2 peri in May 2018, where on the 19th of May, the star was at 120 astronomical units and moved at about 2.7% the speed of light. So that allows us to look at the post-Newtonian effects, which are on the order of a few by 10⁻⁴ in V over C. And so that's where we can see, for instance, the effect of the gravitational redshift, the precession of the orbit, etc. So let's look at the Doppler motions of that star, which you of course recorded also, and you can see the very rapid change of the orbital structure of S2 when it goes around peri and moves initially towards us and then away from us, and then moves all of a sudden towards us in its orbit. And when you subtract from these measurements the best fitting Newtonian orbit, then you can see the effects of general relativity. So this is a residual plot where Newton orbit, the best fitting Newton orbit, is at 0 as a function of time. The best fitting general relativity orbit is red, and the data are the cyan black measurements. So clearly we do see the deviations predicted by general relativity at a level of about 30 sigma. So it's a very fine, very precise measurement of GR. Another effect is the precession. Because the orbit is so elliptical, the precession is not continuous. It's basically no precession near apo, and then very rapid precession near peri. So again, if you look at the residuals, which is what you see below, in one of the coordinates, this is the RA, the X coordinate. Newton again is 0. Then the GR or prediction of the GR orbit is in red, and the data are again the cyan data points. So you clearly see that the kink, the deviation, the prograde orbit is clearly seen. We can also see this as an angle on the sky, because after all, it's a precession, and that's shown on the right side. Again, the same thing. Newton gray at 0, general relativity is red, and the data. So again, now we have a definition, a measurement of the effect of the Schwarzschild precession, currently at about 20 sigma. So it's a highly accurate measurement, and that has also very important astrophysical consequences, which I'll describe next. Now, inside of this region, we are still of course, at about 1,000 Schwarzschild radii. We also have traces. The radio astronomers trace radio emission with millimeter VLBI, and see this 3 millimeter VLBI measurement constrains the size of the radio source to be about 40 microarcseconds. The radio emission is very variable. That's why it's very hard, much harder than in M87, to make an image at 1 millimeter. But that is what our radio astronomy colleagues are very much like to do, and I'm very much looking forward to their results, because they can be directly coupled with our measurements to test general relativity again. What we see are highly variable emissions from the radio source, centered on the radio source, but orbiting. So for instance, on the left upper side there, you see one of these so-called flares where the initial state of the emission was the red point. And then as time goes on, over 45 minutes, the centroid of the infrared emission moved around the fiducial center of Sagittarius A star on a sort of a prograde clockwise motion on about 10 Schwarzschild radii scale, which is just outside of the so-called innermost stable orbit, which predicts the innermost region where particles can stably orbit around the black hole. At that point, the motions we see here are about 30% speed of light, about what you would expect from a, if you like, Keplerian, or more formally speaking, coordinate speed around the 4 million solar mass black hole, and consistent with the fact that most of the mass is indeed on the scale of the event horizon scale, as we had predicted. So now, in 2021, we've come a long ways over these 40 years. We've measured the mass of the central object, which Towns and his students and I were measuring back then, on the same order, the same mass, but now much more precisely, and also much further in. We have a measurement of about 0.3% of the mass and 0.1% of the distance to the galactic center, which is, of course, also of interest for other astronomical purposes. We have detected the gravitational redshift to 20 sigma detection of the Schwarzschild precession. We can also test the equivalence principle by looking at different atoms, helium and hydrogen, and show that the local positional invariance is upheld to about 5%. And finally, the coordinate speed, as I described, near the ISCO orbit is indeed is consistent with the orbital speed around the 4 million solar mass black hole. So that's now at 4 times the event horizon size. So there is really not much space for anything about a black hole. Now, the fact that we see such a clear-cut signal of the Schwarzschild precession means there cannot be any other extended mass inside the S2 orbit more than about 1,000 solar masses. That's what that arrow denotes. So we have actually a constraint of, say, any dark matter or any stellar component which might be in there. It's likely that there are some stellar black holes, but not many. Maybe inside of the parity of S2, there might be, say, five stellar black holes. And obviously we are seeing other stars. So obviously there are some more mass, but it's astounding how little else there is. And in fact, if one analyzes this in a quantitative way, one can set a limit on any secondary black hole or intermediate mass black hole to about a few hundred to 1,000 solar masses. So that's very important because that gives us, in this particular laboratory, if you like, an indication of the inspiraling rates one might see in other galaxies in the future with LISA. And it's clear that in the galactic center, at least, this is a single black hole. Now, of course, I will bore you by saying, are we done? Well, we are of course not done because there is so much more to do. For instance, astrophysics. One of the things which we do in addition to measure these motions is we look at the polarization of the light of the emission of this hot gas around the black hole, and that is highly polarized and varies in light intensity, but also in polarization degree and direction. And the lower left picture shows you that the polarization direction loops on the same orbital time scale of about 45 minutes as the orbital motion. And that is strongly indicative that the magnetic field configuration very near the event horizon is poloidal and not toroidal. It was expected to be toroidal if the density in the accretion zone around the black hole in the accretion disk, if you like, would be dominating. But in this case, and also I should say in M87 from the event horizon measurements, it looks as if the magnetic field intensity is so strong that it dominates the pressure in this innermost region. Very interesting, because that is not what was generally expected in such regions. And that means that, in fact, the energetics of the innermost region may very well be controlled by the rotation of the black hole. More to come here, because such measurements can only occur rarely when you have a flare, which happens typically only once every 2 months. And the probability to see a strong flare is fairly rare. And we are not done, because we want to, in fact, test that the space-time is truly that of a curvametric. The current measurements show that any deviation from the curvametric, which in this case is written in the so-called no-hair theorem, where the quadrupole moment is written as a function of mass m and spin a, where the nuisance parameter epsilon in general relativity is 0. So we know that from current measurements of these flares, but also from LIGO, that epsilon is less than 1, but not substantially so. In our case, because the measurements are not good enough yet. In the case of LIGO, it's because in a stellar black hole in spiral, you don't have much time. You have only about 100 millisecond time in this innermost orbit before the two black holes merge. And that doesn't give the LIGO people much time. If you have gravity and EHT, and if indeed the EHT colleagues would see the same kind of donut emission in the galactic center, then we could probably push the limit to about 0.1. If there were a pulsar near the massive black hole, well, then the timing of the pulsar could push that to 0.05. Unfortunately, no such pulsar has so far been seen in the galactic center. My personal favorite is the ESA mission LISA, which in 20 years' time should be able to measure extreme mass ratio in spirals of stellar black holes into a massive black hole. And that gives a lot of time to see these innermost in spirals and measure very precisely limits on epsilon. And that should be a signal noise ratio of 100. And that would be the time if we indeed can exclude any deviations from general relativity, where we can say we are done. Of course, then there's still the question of the quantum effects, and whether at some point on the way, we might see the fumes, the quantum fumes coming out of the black hole. Well, I hope I've shown you that this field, this journey of 40 years was a fascinating journey, and that it's ongoing, and it has captivated us. It's captivated many colleagues, and that's what it takes. This cannot be done by an individual person, and it has really kept many of the young people in my group, but also in the other institutions and at ESO busy and excited about general relativity, the Galactic Center, and how nuclei of galaxies work. Thank you very much.
Well, thank you very much indeed. You should multiply this applause by a factor of more than 100. Wonderful work, wonderful talk, Reinhard, really very impressive. Now to the participants, most of you know there are two ways to ask questions. One is to type your question in the chat, and then I will read them. Or you can raise your hand, and then Willy Weffler, the IT person at ESI, can switch on your microphone if you like. Now, There is already one question in the chat. Let me read it from William Wall. Hello, Reinhard. Could you perform similar observations for hypothetical massive black holes in the Magellanic Clouds? They are further away than the galactic center, but not as far as many other galaxies. Maybe in M31 too?
Yeah, no, that's an excellent question. I would say there's a whole set of possibilities. The first one would be, in fact, I should say, looking for intermediate mass black holes in globular clusters. And that's something which is on our menu list for an upgrade of gravity, Gravity Plus, which we are currently undertaking. I haven't thought about the Magellanic Clouds, but of course, initially you would have thought, well, chances to see a massive black hole there is not so high, but it's a possibility. M31, unfortunately, is out because it's in the northern hemisphere. And the interferometry we are undertaking really can only be done within about 1 air mass of the zenith. So you cannot go like in radio astronomy very far off. So that's not possible. But yes, other galactic nuclei are very much in our focus. Currently, we are doing this through the measurement of the kinematics of broadline gas. So we've published already one result where in the famous 3C273, we measured the black hole mass from the motion of the rotation in the broadline region. And we have another 5 such quasars already done. And with this already mentioned upgrade of gravity, where we increase the brightness by another factor of 100, or the faintness, I should say, and the field of view, we hope to be able to measure black hole masses to redshifts of 2, okay, and actually do cosmology with that. So I would say we've broken with gravity a major barrier in optical and infrared astronomy at the milli and submillimetre arcsecond level, which had not been possible at the very faintest levels, and also at the very highly precision micro arcsecond level in astrometry.
Thank you. There's a raised hand by Roger Bonnet. Roger, you can switch on your microphone now.
Hello, Roger.
Hello. No, it's always a fantastic pleasure to listen to you, really. But this one is the best I have ever heard from you. It's so many. There are so many things which I am so sensitive to. The role of technology that you emphasize constantly in astronomy is essential, and you are a living example of what we can get with that. I think it's fantastic. We also, I'm very impressed by your taking LISA as a future example. I think what you have done with the black hole here, with all the instruments, all the technologies, give me a good hope that finally the 21st century will be the astronomy of what you did and LISA, and I think it's very essential. Now, all what you did was not possible with a lot of management of people. You have been dealing with people and people and people, and you have shown them on their pictures, and all of them are smiling. So they really enjoyed working with you, and I'm not surprised because you are really one of the fantastic winner of the Nobel Prize. Thank you.
Thank you. Thank you, Roger. I mean, I can, of course, say that it was a pleasure to work with you when working on ISO and preparing for Herschel. And I think, indeed, I very much think that ESA now is in an excellent position with LISA to do, the crowning, the culmination of this kind of work in the next 20 years. It'll be hard, but it's possible.
There's a question in the chat by Massimo Cappi. Thank you for this very interesting talk and impressive journey. A question, do you see any evidence in Sagittarius A star of an outflowing wind in the innermost regions from millimeter emission or on slightly larger scales in ionized gas?
That's an excellent question, and the answer is so far no. So obviously, the first thing you would want to see is a radio jet, and so far, at least on the scales which had been accessible to study, such a radio jet has not been seen, and believed to be relatively modest in size, perhaps because the accretion rate is so low. I mean, it's about 10 to minus 8 solar masses per year inward into the black hole at any given time. So it's very low accretion rate. Therefore, you wouldn't expect to have much, jet emission. But still, that's something the event horizon people are looking for. I should say the 3 millimeter VLBI, which I showed, is most consistent with a source which is not elongated in any possible jet direction. So maybe there is no jet, unlike in M87. In terms of gas outflows, there's a lot of outflows in the general region, as I mentioned, due to the stars. So we can certainly see motions of gas clouds moving around there of several thousand kilometers per second, but we have not specifically seen anything which has to do with the black hole itself. Likewise, the X-ray astronomers have not seen any broad KAV emission from the center. So it does look as if this, at least here, Sagittarius A is very much in sleep as far as the activity of the black hole is concerned.
Thanks. Next raised hand by Hans Zinnecker. So Hans, you can switch on your mic.
Can you hear me?
Yes, Hans, how are you?
I'm fine. I'm in Chile, and I really greatly enjoyed the talk, and because you always give up to the latest moment the results, so these gravity results, these recent ones, in times of pandemia, is quite impressive. Great.
Yeah, and who would have?
Yeah.
Go ahead.
Who would have?
Who would have thought that 3 years after the Peri of S2, we are observing 3 Peris in 1 year? That's just absolutely mind-boggling, because it tells you statistically that what we are looking at is not the Sleepy Village, but Broadway in New York. And so this is great for the future, in particular for the chance to see a star further in, because then we can see the lens tearing position perhaps and measure the spin of the black hole directly.
Oh, let me recall something. I mean, since I've been in your group in 1990, I remember that I was thinking back, did I really believe in 1990 you would be able to do all this, which you already were trying to achieve in those days? I mean, you had the vision. And I must admit, I was not convinced, but now I have to tell you, you are the wise man, and with a lot of vision, beating most people in terms of vision, and you have the people to do it. So congratulations.
Well,
Okay.
Hans, look, thank you that you say that, but I would make that a little more modest, because first and foremost, I have to be grateful to the Max Planck Society. The risks which we took were so substantial that had we, including you, had to go through peer review every 2 years, we would have not made it. Every peer review would have told us that these stars don't exist. I mean, come on, there was so much theoretical work showing that there should be a dearth of bright stars near a black hole. Very clearly, that's nonsense, the peer review would have said. The fact that the society has given me this long trust and said, go ahead, do it. And even now, where I'm almost 70 years old, getting money to do the next generation, including also the ELT, well, that's something. And I'm very, very grateful for that. It's also the case that this would have not been possible without so many good young people and without ESO. ESO really, in that sense, is a great success story.
Yeah. Okay, okay.
Thank you. Next question is on the chat again. Mark Turler says, excellent talk, thanks a lot. Has the spin of the Galactic Center black hole been measured?
The answer is no, as I just said. It, in terms of the size of the effect of the lens steering position, that is a factor of about 100 smaller than the effect of the Schwarzschild position. So you can see, if we wanted to do that during the next Perry, I won't be able to do that. I will then look at the flowers from below, but others, if they want to use the next Perry in 13 years, then you have to measure yet another factor of 30 better on S2. That's possible, probably with the ELT actually, on stars which have complex spectra. Then you can actually use the spectral information rather than the astrometry. But it's going to be hard. Therefore, it's a much better way of doing this is to find a star inside of the orbit.
Thanks. Next question from the chat, Clovis Dematos. Thank you for the great talk. Have we observed any gravitational waves coming from the center of our galaxy with current gravitational wave detectors, or must we wait for LISA?
Yeah, no, we have to wait for LISA because the current gravitational wave detectors are only sensitive to, about 50 solar masses or so, because, the frequencies of the LIGO type instruments only look at the high frequencies, while anything in the Galactic Center would have low frequencies, and that cannot be done from the ground.
Thanks. Ari Laor asks, thanks for the most inspiring talk. Is there evidence for counter-rotating stars with respect to the galactic rotation?
In fact, I should say that the early type stars, the Owen Wolf-Rayet stars, there is one clearly present disk structure, which, as I said, is rotating in a disk plane, although it's thick. That angular momentum is already retrograde relative to the galactic center or the galaxy. So that tells us, perhaps not surprisingly, that the gas which we see in the central region is not galactic rotation, because if you have an angular momentum which is different from that of the galaxy, your chances to have a shock and collision with another gas cloud is high, and then you fall in. So that's the most likely situation. The motions of the central B stars, as you may have seen in the movie, are completely random. In fact, they are also not only isotropic in direction, but they are they're hotter, more eccentric than a thermal distribution. And that we ascribe to basically two-body effects or three-body effects in a binary or binaries, which are shot in a lost cone orbit into the black hole, the so-called Higgs. My God. Anyhow, effect which you would expect if you shoot binaries at the central black hole.
Next question in the chat, Alexander Sakharov. Thank you very much for your excellent talk. Could you tell a little bit more about the contribution of Charles Townes in the development of AO, if it was such a contribution, of course? Thanks in advance.
No, Charlie did not look at AO. That was he knew about it as far as the military is concerned. As you probably know, that in the United States, the adaptive optics efforts initially were confined to the military, who wanted to basically take sharp pictures of USSR satellites. He knew about this, but he felt that was not an appropriate kind of development for a university group. Townes very much wanted to work with students, and the kind of more extensive, larger efforts he felt was not what should do at universities. So that he knew about it, but he didn't work on it. He worked at longer wavelengths. So the basic work he did was at 10 microns, where you don't need any adaptive optics really anymore. And the diffraction, indeed, you can get through normal techniques.
Thanks. Thomas Redman writes, thanks for the excellent talk. Would one expect some signs of interaction of the stars with the gas around the black hole in their spectra?
That could very well be the case. And we think we have seen such an effect. In 2010-11, we discovered an object which was coming in on a very radial orbit with an ellipticity of about 0.97 or so, which came closer and closer. It was initially looked like a star, but then we saw that the gas emission in bracket gamma was getting elongated in spatial dimension. So at least in some parts of it were gas-like, and the gas was basically getting tidally stretched. There may also have been a central star, that may very well be, and there's a lot of discussion about this. Now, this object we call G2 tarried in this innermost region, in fact, at 1300 Schwarzschild radii in 2014, and then went back out. And then the centroid motion, which was up to that point Keplerian, slowed down. So if you look in a paper by Gillison et al. In 2018, we now show very clearly that there was an interaction of the object, the gas in the object, with the surrounding medium, which can be interpreted as friction. From that, you can actually infer a density. And if you extrapolate that density to the center, then that's consistent with the amount of Faraday rotation the millimeter astronomers are seeing. So I think we have seen these kinds of interactions, yes.
One more question by Hans Zinneger in the chat. Great talk, even with the latest gravity results. My wild question today, can the black hole in the galactic center acquire some charge by differential accretion of protons and electrons? Can the black hole, despite the no-hair theorem, have a rotating magnetic field affecting the accretion disk?
Well, okay, I think there are charges, Hans. I mean, the region in the innermost region is obviously a plasma. And in fact, if you look at Roger Blandford's work as an example, then you can see that the energy density in the magnetic fields structures near the event horizon, or just outside of the event horizon, has such high currents and energies that the vacuum starts to produce particles out of the vacuum. So absolutely, there will be charges, but it's not that the black hole has a net charge. Okay, it's just that there are, lots of charges around it, which in fact then flow along the magnetic fields.
So I don't see any more raised hands or typed questions. So let me announce again next week's talk by Corinne Le Carré from University of East Anglia, UK. She will talk about the contemporary global carbon cycle and the impact of the COVID-19 pandemic on CO2 emissions. I'd like to thank all participants. There are still 74 online, also the active questionnaires. I'd like to thank ISI staff, all of them, in particular Willy Weffler and Andrea Fischer for the support of this Game Changer series. And 100-fold thanks to Reinhard Genzel for really a wonderful talk, wonderful work, wonderful answers to the good questions. Thanks, Reinhard. It was a great pleasure to have you.
Thank you, Joachim, for having me. Wonderful. Goodbye.
Bye-bye.